Guys, it's our first reactor design problem. Here we go. Besides the other one before this, but this one actually has to do with a reactor itself. So let's do this, okay? We got this. Okay, so the first thing you do when you do any of these problems for any of these tests, you have to find out which reactor you're dealing with. So isothermal and well-mixed batch reactor. So they gave us two things. They said isothermal, and they say well-mixed batch reactor. So what do I get from isothermal? Well, I get the K is a constant, because the rate constant is dependent upon temperature. It's a function of temperature, and if temperature is constant, the rate constant is constant. Rate constant is constant. Okay, the next thing is, well, mixed batch reactor. That basically means that the reaction rate anywhere in the reactor, if you looked anywhere in the reactor, it's going to be constant, because everywhere the concentration is the same. And as you know, the rate of disappearance of A is a rate constant times, in this case, it's going to be first order. So the concentration is the same everywhere else, everywhere in the reactor, so this will be the same everywhere in the reactor. That's the way to think about that. Now, you're dealing with first order elementary liquid phase reaction, so it's going to be KCA. Okay, so let me drop down over to the right over here and write down all the variables that were given. So the initial concentration of A is 10 moles per liter. So they give you the destruction of A, which is right here. We have it, but I'll write it anyway. RKCA. And they give us the rate constant. Calculate the concentration of A after 90 minutes. Okay, so T is equal to 90 minutes. That's how long our reaction is going to go for. Okay, so let's keep these in mind. I'm going to clear up some room. I might leave the box there just to keep in mind it's a batch reactor. And we'll do our analysis. So the first thing you do is you do a material balance. In minus out plus gen equals accumulation. Now in terms of a batch reactor, like I said in other videos, nothing goes in, nothing comes out during the time of 90 minutes. So you're in and you're out because you got a lid on your batch reactor. This leaves you with a generation term equal to accumulation. Now what do we put in for our generation? Now it was a long time ago I did this in a video, but that's going to be the rate of reaction times V. And then the accumulation term is going to be the derivative of the number of moles of A over the number of moles, or not the moles, but the differential time, right? And you could refer back to that first couple of videos I did on batch reactors where I discussed why this formula makes sense. Okay, so we're solving for time. So are we giving initial amount of moles? No, we're not. We're not even given a volume, so we couldn't get the initial amount of moles. But we can make this whole formula in terms of concentration by dividing volume to the other side. Right? Okay, so we move down this way. Since V is constant, the volume is constant for a rigid batch reactor, we could put that into the differential term. Right, by dividing NA over V, you're going to get CA. Okay, moving forward, now we got this equation. Now that's something we can solve, right? So let's plug in our first order reaction into RA. Remember, this is positive RA that we have here. So what we're going to want to do is put in negative KCA, because negative RA is equal to KCA, and therefore RA is equal to negative KCA. And here we have a positive RA value. So negative KCA is equal to dCA over dt. So push dt to the left side and push CA to the right side. So then what you end up getting is this. Alright, so we're almost there. So let's integrate negative k from 0 to t dt. It's going to be integral from your initial concentration that you added, which will be higher than Ca, right? Because you're losing A. And this would be dCA Ca. Now if we do the integral, I'm going to right arrow to the side, you're going to get negative kt. It's going to be equal to the ln of Ca over Ca sub naught. Now to get rid of the natural log, you got to put both sides as the power of e. So in this case, e negative kt, and e to the natural log of Ca over Cao is just going to give you Ca over Cao. Now what we want is we want this whole formula in terms of CA, so we can plug in the time we were given and simply get a concentration after 90 minutes. Okay? So multiply CAO to the left-hand side, e to negative KT, is equal to CA. So let's bring down our variables that we know. We know our K, we know our CAO, and we know our T. So, good thing I'm using OneNote. Okay, copy this, bring it down here. Easier when you're doing paper on the test, believe me. Okay, now, these are our variables. So let's do 10 moles per liter. And remember, keep the units alive because you're going to see it might make a big difference. And it does in this case, it does. Negative 1 over hour right here. And this is going to be 90 minutes. So let's convert minutes to hours. So that's going to be 1.5 hours, right? So this would be 1.5 hour. Now the units make sense, and it'll actually give us a concentration in terms of moles per liter. So then let's do this. What's it? Negative hour. So negative 1.5 here. You go CA. Now I'm going to do this in MATLAB real quick. That should be negative. There you go. 2.2313. Okay. I hope this helped, guys. Make sure I did it right. Yep. Everything's good. So this would be your concentration. And what units do you have there? We have moles per liter. Per liter over CA. Now it's important to analyze, does the answer make sense? Well, I know that the final concentration should be less than initial concentration, and indeed it is. It actually cut down, let me use colors. It cut down by 1/5 approximately. So 2.313 moles per liter is equal to CA. Does make sense. And I always check in this class, in the answers, make sure it's the right decimal places. So it should have been 2 decimal places. So 2.31 is really what you should have gotten. Okay, I hope this helped, guys. See you next video. We'll do even harder ones. Push on, guys. Alright, see you guys next video.